The implementation of aerodynamic theory for the improvement of voltage consumption in the dielectrophoretic systems, by Alberto González, Ana Sagahón, Erika Cavazos, and Ricardo Hernández. Material characterization, as the name implies, is the process by which key characteristics of any given material are found and registered. Similarly, when the characteristics of a range of materials are well documented, characterization tools can be used to determine the material being tested. Dielectrophoresis is one of these tools, and it is the process by which small polarizable particles, usually at the micro or nanoscale, are subjected to an electric field, which induces an electrokinetic force which accelerates them in the direction of this field. Electrophoretic techniques have also been adapted to other applications such as the determination of protein isoelectric points. It is known that the electrophoretic mobility of a particle is proportional to its zeta potential. Therefore, particles with the same size but different zeta potentials can be electrophoretically separated. Insulator-based dielectrophoresis is usual technique, and it is achieved by using electrodes to induce an electric field on a medium on which particles will travel, and insulating obstacles that cause this field to become non-uniform. The non-uniformity is required for the polarization effect which drives electrokinetic forces. This novel approach allowed for the use of pure DC electric fields, and for the first time the competing forces of electrophoresis and electroosmosis were analyzed in the presence of dielectrophoresis. Here you can see an schematic diagram of dielectrophoresis versus electrophoresis. A shows positive dielectrophoresis effects, where the dielectric particles move towards the high and low electric field gradient, respectively. And B shows electrophoresis, in which cations and anions move towards negative and positive electrodes, respectively. The dielectrophoretic force applied to a homogeneous sphere of a radius in a suspension medium of a relative permittivity can be demonstrated by the next equation, where omega is the angular frequency of the applied field, delta E denotes the electric field gradient, and Re times K times omega is the real part of the Cm factor.
Process of modeling. For the model, we used the computational software COMSOL Multiphysics. We began the project with a 2D model with a stationary simulation and add the electric currents physics module. The unit of measure was set to micrometers. We begin the design with the water channel in the shape of a rectangle with center in 0,0. The values for the electric conductivity was set to 5.5 e to the minus 6 and a relative permittivity of 78. 850 micrometers were used for the height and 10 to the e to the 3 for the width. For the insulation domain, the material selected was polydimethylsiloxane, in the shape of a rectangle as well, enclosing the water channel, which at the center we find the insulator obstacles in the shape of an ellipse. Therefore, these obstacles have two diameters. For the A-axis, the size corresponds to 75 micrometers, and for the B-axis, 188 micrometers. We need to keep in mind these measurements since they have a big influence on our results. The electrical conductivity of the material is 2.5 e to the minus 14 and a relative permittivity of 2.75. Finally, we have the conductors, set as electrodes in the shape of two circles of radius 350 micrometers, each one located on the extremes of the channel at a distance of 4,500 micrometers from the center. The material used was platinum. The modules of the electric current physics used were electric potential on the left electrode with a value of voltage input equal to 1000 volts, and ground on the right side with a value of 0 volts. The information of all materials were obtained from the COMSOL library.
Obtention of results. First, we used COMSOL. COMSOL is a powerful program of CFD. CFD is computational fluid dynamics. This is similar to finite element method because you have a system. In the system, you need to add a mesh. In some programs, you can modify the geometry of the mesh. In this case, we have an auto meshing because the program used only triangles in the geometry. This is maybe a little problem because maybe the results can be affected, but they are very small. And when you have the mesh in all the system, basically you have all your boundary conditions. The size of the mesh is very important. It's not necessary to have always a small geometry size because if you have the small size, the computer will work more and it will be more time of compute. So one of the strategies is to mesh with bigger size the parts that we don't care, and with the smaller size the part that we want to analyze. After meshing our system, we got similar results. We simulate and we got the electric potential, the electric field, and the electric gradient. We can observe the direction of the electric field, and this is similar to the other results. We made some changes in our project. We changed the airflow in the column. This change reduced the resistance in our circuit, and if you have a constant voltage and you reduce the resistance, the electric current will increase. And if the electrical current increase, the current density increase too. And if the current density increase, the electric field will increase too because the conductivity of the material is the same.
Before we can begin explaining and discussing our results, we need to clarify one important aspect in our investigation, and that is that in both cases, both with the original model and with our improved geometry model, the same study was done on the software. The only difference between these two being the input voltage used to create the dielectrophoretic forces. In the original model, we used 1000 volts, and in our improved model, we used 700 volts. This is to prove or disprove that with our new geometry, the required voltage is actually lower. The first result we're going to analyze is the electric potential distribution along the channel. Here, we obviously expect at the beginning of the channel in the input electrode, the voltage to be at its maximum value, and at the ground electrode to be at its lowest value of 0. Here we can observe how, with each post or line of posts, there is a voltage drop. However, what's important here is that both in the original model and in our improved model, this behavior is the same, which seems to indicate that the change we apply to the geometry of the post does not cause any unforeseen or undesired consequences with the distribution of electric potential along the channel. The second set of data results we're going to analyze is the graph of the gradient of the electric potential. And here, the main thing to remember is that this gradient of electric potential squared is directly related to the dielectrophoretic force that each particle in the solution experiences. And as we can see from these graphs, although not major, there is a significant improvement in the magnitude of this gradient in all of the post arrays in our improved geometry when compared to the original one. Finally, we get to the third and probably the most important result in this investigation, the electric field distribution along the microfluidic channel. This is the most important because the whole objective of this investigation is to figure out a way to improve this microfluidic channel in order to reduce the voltage requirement needed to generate this electric field at the trapping sites in order to induce the dielectrophoretic forces. In both of these graphs, we can clearly see that in our improved model, even with a reduced input voltage of 700 volts versus 1000 volts of the original model, we can obtain in these columns of insulating posts the same, if not a higher magnitude for the electric field, which obviously points to a reduction in the required voltage needed to generate these electric fields and deems our investigation and our improvements a success. This improvement could be further increased with a more reduction in the width of the elliptical obstacles. However, this is obviously limited by the manufacturing capabilities of the lab that is doing these studies or analysis. So, now that we've seen that this new geometry we propose does improve upon the required input voltage to create strong enough electric fields at the trapping sites of microfluidic channels to induce the electrophoretic forces, what can we do with this information? What's next? Well, the first thing that comes to mind are point-of-care systems. In point-of-care systems, you need to be able to carry or to travel with the whole system of analysis to where the patient is or where the person of interest is. And obviously, this puts a big challenge on logistics on providing large amounts or large magnitudes of voltages. So, if we previously needed equipment that could provide 1000 volts to supply these dielectrophoretic forces, now we need less voltage and so maybe less expensive equipment or more accessible equipment. This could also mean that these techniques could be used permanently on organizations such as remote laboratories or remote clinics, where we could bring these analysis techniques and bring medical attention or any kind of special attention to people on more remote places. It should also be noted that this improvement or reduction in the required voltage can be increased by, as previously mentioned, reducing the width of the elliptical obstacles in our insulating post of the microfluidic channel. However, this can also prove to be an obstacle in manufacturing, especially when we're talking about these remote laboratories or off-site laboratories and point-of-care systems. So this is an avenue of future research to figure out which is the limit at which we can manufacture slim enough post to reduce the voltage to the maximum level possible, or the minimum level possible, sorry, at the same time that it is manufacturably possible.